Maybe a short day for everybody. Okay. So recording is in progress. Shrinkify that to share my screen. Okay. We're now all good in recording. Let's get to our class, which is I don't think I have the syllabus updated, but today's lesson in lab is going to be, see, 14 was vectors, and yeah. Oh, so this does appear to be updated. So the lesson looks like it's linking correctly. And these labs are wrong. So you'll have to either take it from the course notes or from the Blackboard link, because I put the Blackboard link up last night, I think. And if I'm wrong in line, we'll fix that during today's lab. All right. So we want to go to 11, databases. So today's topic is databases. This first one is just some background terminology jargon, and then we will get to data frames, which is a way of representing a collection of stuff that's somehow related. And we'll introduce the external package called Pandas, which is the tool that's used in Python scripting and Jupyter notebooks to manipulate databases. So our objectives today is, hopefully by the end of lab, you'll understand a data frame abstraction, what it is, and be able to implement and manipulate data within a data frame using the Pandas library, and be able to obtain some basic statistical measures of data. By basic statistical measures, don't have a KOW and worry about statistics. So things like the mean value of a column, standard deviation of a collection in a column, that kind of stuff. So as far as statistics go, not too deep. We'll go ahead and go deeper later in the class so that you will ultimately hate statistics as thoroughly as you will when a statistician teaches it, but at least you'll be able to get numbers. So the main thinking concepts involved in databases are abstraction and decomposition. Abstraction, which is to represent a collection of related things in something that we can talk about in a computational sense, and decomposition, breaking those things into smaller subsets. So my feeble attempt to represent a database and its relationship to decomposition. So imagine we have an automobile, and any motorheads out there recognize what kind of car that probably was. So I'm thinking a Yugo or a Volkswagen Rabbit first generation, or a Fiat Panda, which you can't get in the US. So here's some car that's been disassembled to all its component parts. This is why automotive repair work is so damn expensive. Because if you need to replace that part's probably buried in some other assemblies, and they can't find it. And then in all things, there's a whole lot of extra parts there. So anyone that's worked on your own car knows that you can leave half the parts off and it'll still kind of run. So if the location of each part is recorded, if you know where everything is in a geographical sense, then it's easy to determine if something is missing. For instance, I have made a driver's side front quarter panel disappear by hiding it behind a bluish cloud and a wheel. And that is fairly important in logistics and managing collections of many things. So a car is literally a collection of many things It's all operating in formation. Just like a helicopter is a whole bunch of metal parts moving in formation, so is a car. So it'd be pretty evident on a fully assembled car if those two parts were missing. If it's missing the rear wheel and the left front quarter panel, that'd be obvious. But smaller parts are harder to track. And so we use database management tools to help us track those little parts. Now, what does that have to do with computational thinking? Nothing yet. I'm trying to motivate the value of a database. So if we considered the cars themselves, they're a fully assembled object, but they could represent a database scheme. If fully assembled, you can put it here, and anytime you need it, you can recover it. Now imagine if you had two fully assembled cars, and we moved one of them. And again, if you've ever worked on a car, you've heard the disgusting sound of as a ball bearing falls out of somewhere. And if we had a database management system that had each part indexed, we could figure out by a simple query. Basically, we ask the ball bearing, who are you? What's your part number? Where do you belong in terms of a computational thinking context? And the database returns that information. And then we can make the decision to try to put the part back where it belongs or ignore it. And that's not as silly as it is. So one of my automobiles is a 1994 first generation 4Runner 4-wheel drive thing. So I've got an instrument panel that was always shorting out, and the lights came on and it kept sending a code. My code reader can't even plug into the thing because the connections have changed since the 90s. So I took it to the mechanic, and it's like, I'm getting this error code, and the best I can figure from online is that it means there's something wrong with the braking system, but I've got brake fluid in it. I've already bled them. And so he took it apart, and that cost some money. And he says, yeah, you have a short in that lamp. The problem is I can't get replacement parts. So we go to pick apart and try to find one that's been wrecked, that's close to the model year, or we can simply leave the lamp out and not fix the short, put caps on the end of the wires so that there's no electricity going through that. So I said, yeah, we'll go ahead and do that. I can function without a light that comes on that tells me I've left my parking brake on, because they have a special backup feature in older automobiles. If you leave the parking brake on, it's a manual transmission. I usually can't get it moving. If I do get it moving, it has a olfactory indicator. After about 3 or 4 miles, you can smell that you've left your parking brake on. But that's an example of making that decision of whether or not the part's important. But we have to know what part it is. So in other contexts, we wouldn't necessarily want to take the car apart and store it in a bucket every time we wanted to park it in the garage. In that case, we want to store the car as an entirely assembled unit, as an entire database. So the database itself is the garage, and access the pieces through it that way. So again, with used cars as an example, if you are getting a part for an old car that you can no longer get an OEM or an aftermarket replacement part for, which anybody know what the federal requirements are for automobiles? How long does the manufacturer have to make and supply parts? 10 years. So if you have a 25-year-old car, it's quite likely you can't find parts for it. But most people wreck their cars. So if you have a 25-year-old car that's still running, chances are 90% of the same model year has been crashed into something. And you can go to a auto parts place like here in Lubbock at Pick Apart. I don't actually know what the name of it is. And they might have several copies of your vehicle laying out there in the yard. It's not profitable for them to disassemble it and put it in a parts bin, although that would make some sense on a bigger scale. But they'll let you go out and look for the part, and if you can find it, then you negotiate how much they're going to sell it to you for. A database would make that easier, and they likely maintain a database of the parts they've sold by vehicle VIN number that's laying in their wreckage lot. Now, car parts aren't the only people to do that. There's this organization that flies airplanes, And those are pictures of some B-52, I don't know, C or Series D model that are laying out in the desert. So they were cut here by a treaty with, I think that was Soviet Union at the time, part of some strategic arms limitation talks. But other than that cut, which makes that particular airframe unusable, supposedly, but a good person with a TIG welder could weld that thing back up and get it back in the air and drop nukes on Ukraine or wherever, no problem. Boeing doesn't make parts for B-52s anymore, yet they are still repairing them. Where do they get the parts from? They have a database of every airframe that's been cut and each part that came out of it, so they know what's left. And they use that to cannibalize and extract spare parts. And that's not just a picture from recent history. Here's a picture from the end of last month, January 22. So they grabbed one of those airframes there that was not cut up as part of a treaty requirement, and they're dragging it to Oklahoma, and they're going to make some changes during modernization efforts, and they're just using this old thing as a way to test how to do the installs. Because fixing a perfectly good working airplane by putting a new part in it somewhere, it's not a matter of just pulling a panel off and doing it. You try it out on one where there is no huge risk of failure. So all those seemingly unrelated pictures, those are all very intimately related to the idea of a database. So the database is a container for data. So there's a database of B-52 bombers that the Air Force still owns. They operate 68 of them, I think, are still currently operational. They have hundreds out there in the desert, and they rip those apart to keep those 68 still flying. That's all because they have a database of those, of every B-52 ever built, when it was built, each of the serialized numbers. Same thing with cars. Same thing with your bank accounts. How many Amazon Prime members here? They know everything you've ever bought to before you were even born. So they have the ability to use that information to predict what your next most likely needs are. Walgreens has that information. Kmart used to, but they managed to go out of business. So database management systems and database manipulations are a huge deal in the business world, in the engineering world. Take engineering as an example. Imagine a bridge. So y'all imagining a bridge? Are you imagining one made out of concrete probably? If you've lived most of your life in Texas. So you're imagining concrete uprights and then concrete beams. Those are all serialized. Every one of those that's ever been manufactured relatively recently. The 50-year-old bridges, they don't know shit about. They know when it was built, what yard built it, how it got transported to its current location, and use that information as a way of telling when to do repairs, or more importantly, how to manage their plausible deniability when the thing falls down. So databases are a big deal. Okay, so now that I've made the pitch that these are important, what is a database? It's simply a container for data. So we could argue that you've already seen databases in this class. A database is like a list, which is a container for data. And that's true, that's a true statement. The difference between a list and an actual database is pretty minimal at its lowest level. A public library, for instance, stores books. The books themselves store letters of an alphabet, and those are arranged in such a way to come up with thoughts. So the library is a database of books, and that's a legitimate statement. But strictly defined, the databases we're talking about are computer structures to save, organize, protect, destroy, and deliver data. A system that contains such databases is usually called a database management system, and the acronym is DBMS. And so you can think of it as an electronic filing cabinet. It contains digitized information, which is the data, which is kept in a persistent storage of some kind. So databases by design are intended for the data to be very difficult to destroy. That's why if your name comes up on an FAA no-fly list, and it turns out that that was a mistake, that it got put there, it's nearly impossible to get it removed from the back-end database. I think it is impossible. So they give you a redress number, which means we know you're not allowed to fly. There's some reason that you are allowed to fly if you have the proper redress number. And then they track you and you get profiled when you go to whatever country you land in, strip searched. And the good thing is you get a physical examination, Matt. They tell you your health is fine. Here, go ahead and put your clothes on, move on. He's laughing. Thank you for laughing at my very piss poor joke. So by design, the data is intended to be very difficult to destroy. It's not supposed to be impossible to destroy, but if it's a federally operated database, you can be guaranteed that they're incapable of destroying it, because there's always that fear at the federal level. Maybe we can squeeze some money out of taxpayers by keeping that piece of data around. And if in the case of a no-fly list, they certainly can. Okay, so persistent storage. So we design these so that we can add new information to the database, presumably delete, change, and retrieve existing information. Although, like I've just said, the deletion is intentionally difficult. Although destroying an entire database is really easy. By issuing requests or commands to the software that manages the database, which is the database management system. And those requests go in the common name of a query. That's just a jargon for sending a request to a database management system. So you query it to get data out, you query it to put data in, you query it to destroy a piece of data, you query it to back something up. They use the word query as run this cell. So in our class, I always say run the cell or execute the code cell. In database management world, that's issuing a query to the database. So when you see the word query, don't get all confused by it. It's one of the few words that begins with Q in the English language that we use relatively frequently. So in practice, those user requests are formulated in a variety of different ways. Sometimes by pointing and clicking on a clicker doodle with a mouse, other times by actually typing text strings. It's probably best for, if this is your first time hearing about these things, to think of them as we're actually forming simple text string commands in some formal language. So for example, if we had a human resources database, we might issue a command to the database management system of something like EMP where job equals programmer. So employee database, we want to find the job titles programmer, and then presumably we want it to list out all of those. And so that's what a structured query language like command looks like. Now that one may not be an actual SQL command that would work, but that's what they look like. Identify the database, you identify the table, you identify the thing that you're looking for, and then what you want it to find. Just like in our NumPy arrays, you identify the array name, you identify the index of the thing that you're looking for, and then it returns the value. So that particular expression is a representation of a retrieval request. And we're asking for employee information for employees whose job title is programmer. And then once we submit the query and we get a return, that whole activity, submit query response, is called a transaction. So you can guess where databases first made their big hit in the world if it has the word transaction as one of its jargon words. It had something to do with money. Okay, so let's look at some of the different types of databases. There's actually not that many. The simplest form of a database is a text database. So when the data are organized into a text file in rows and columns, kind of like an array or a list of strings, it can be used to store, organize, protect, and retrieve data. Saving a list of names in a file, starting with the first name, followed by the last name, would be a very simple database. And if you have a database like that, I dare say every one of you does. If you own an employee location device, or you have a family plan with an ELD, employee location device, or taxpayer location device, I like that better, a TLD. You probably have a list of contacts in it. That's a simple database. How many of you all memorize phone numbers anymore? I would guess, so a few of you memorize some. So back when I was your age and dinosaurs roamed the earth, we didn't have these kind of databases that lived with us. Occasionally we would write phone numbers down, but most of the time you memorized 8 or 10 of them. Your home phone, then they invented 911, so you didn't have to figure out the police, ambulance, fire in your community. That worked everywhere, except if you're overseas, and it's 311, depending on which country you're in. Home phone, 911, usually a couple of best friends, and maybe a store where your car was being repaired. Most humans can remember 9 or 10-digit numbers pretty effectively. You get much beyond that, and your memory goes to crap. So we had these little pieces of paper that had letters of the alphabet on them for last names, and then it was wrapped in a cover, and they were usually black. So they were like little black books, and you would trade them at bars. So that was the database too. But modern ones are way better, because once you get the phone number in it correct the first time, you're good to go. Until the phone falls out of your pocket into the toilet. And I don't know about you, but cell phones and water, they don't mix so good. Green stuff oozes out. That's the battery dying and taking everything it can with it. And if you haven't done a recent backup to your computer or your cloud account, all that information is lost forever, which is a shame. So if nothing else today, back up your phone this afternoon, just in case, before you drop it in the toilet. Okay, so who's dropped a phone in the toilet? Ever? Even if it's someone else's phone, which is way better, but okay, just warning y'all, it's gonna happen. Maybe not for a lot of years yet. All right, so that was a simple database. You would update records in that simple database by changing specific names. You remove entire rows by deleting the lines, and you can add new rows by adding new lines. That would be a simple manifestation of a database management system. Not terribly sophisticated by today's standards, but quite useful for the needs of keeping track of people's names and phone numbers. And typical terminology kind of database would be called a flat file database. I'm not sure why it got the word flat. Maybe single file would have been a better terminology. But if you hear someone talking about a flat file database, the best mental model you have is an Excel worksheet with just one tab sheet, not multiple tabs, just a single Excel worksheet, or a single NumPy array, or a single list of lists is a flat file database. Then we come up with better ways, which is to use a relational database. And what a relational database is, for example, Microsoft Excel is just a spreadsheet program that has multiple tab sheets available. Microsoft created the Access Database Management System, which we always joked in the early 1990s, around 94. That was Microsoft's way of making Excel useful. Access was a piece of crap, and so they had to build it on top of Excel. Those are good examples of desktop database management programs. And the value of that is that first made relational databases available to most people. And a relational database is the most common type of modern database system. And what it contains is multiple tables of collections of data. So think of multiple flat files that are somehow related to one another through special key fields. And a field in a database, if you imagine a spreadsheet, again, is that mental model. Each row of the spreadsheet in database jargon is called a record. each column of a spreadsheet analog is called a field. So for example, your contact database in your phone has a record for every entry. It has a field for last name, first name, cell phone number, home phone number, web page, maybe a scoring thing for how much you like that. So that's the difference between a record and a field. And in databases, you'll hear those. So the relational databases are far more flexible than flat file structures, and they provide greater functionality for reading, creating, and updating data. And they almost all use a variation of something called structured query language. A structured query language is sort of kind of like a Python or Fortran or C++. I mean, it's a computer language. But it's taken on a bigger role. It means a type of language for accessing databases. So SQL in MySQL running a Maria database backend is going to look slightly different than SQL, MySQL running, forget what the other major, an Oracle backend. They're going to be really close. And so once you understand what a structured query language looks like, you would be able to diagnose something in one and make it apply to another. But it's not necessarily a single language. It's a kind of language. And the kind of part of it is that the queries are constructed almost uniformly in the same way. So the construction is identify the database, identify the table, identify the field in the table you're looking for, identify the condition you're testing for, tell it where to put the output. And so a structured query language instruction, they almost all look like that. All right, some examples of relational database management systems are SQL Server, SQL structured query language, Oracle database, Sybase, Informix, MySQL. MySQL runs on top of a lot of different back-end databases. The two major ones are an Oracle and Maria. And interestingly enough, they were both created by the same person, not working alone, but in charge of the team. And Maria was the name of the guy's daughter who got pissed off when he was working at Oracle and quit, started his own database company. So that's kind of cool. The relational database management systems are far superior for big databases. So about the most you can store in a Microsoft Access database. You physically can store an unlimited number of records, but store and access in a reasonable amount of time, you're about 50,000 records, which sounds like a lot, but that's nothing. Amazon processes 50,000 transactions probably every 2 seconds. So 50,000 is not big. It's not big data. It does not weigh half a kilogram, which we have established is the weight of big data earlier in the class. So here's just an example to illustrate the ideas of database concepts. Oh, I have time. Oh, I'm kind of babbling a little slow today. So here's a figure that shows a typical database, and this one has to do with suppliers, parts, and shipments. Now, if you think of buying stuff predating the internet, but even on the internet, that does not appear to be a whole lot of information. So that's a fairly high level of abstraction. We have a supplier number, S1 through S5. We have a contact name, Smith, Jones, Blake, Clark, Adams. We have a status. I don't know what that means. And we have where the particular supplier is located or the warehouse is located. Then we have a part number database, which is database or table P, parts number P1 through P6, part name, nuts through cogs, part color. I don't know the utility of that, but they've got the colors listed and then how much it weighs and then where the parts are located. You notice that the part database and the supplier database, what fields do they have common? close. The city is the only common field in those two tables. And then the last one is the supplier part. That's the shipment database or the shipment table. And it's telling the supplier number and the part number and the quantity that's either available or on order from each of those places. So those three tables collectively formulate a database, and those three tables would be called a schema. And I don't know why they chose that word. So that's the scheme of this database. So real databases can have multiple schemas inside a single computer storage system. So again, going back to Amazon as a prime example. Damn, I stole that word from the English language too. Going back to Amazon as a fundamental example. They have raw data in tables like this on all of us, everything we've done, even our nefarious web searches in incognito mode, thinking that nobody could watch them. Bullshit. They can reorganize those tables as needed to satisfy their database management requirements. And each of those reorganizations is a different schema. So again, if you're working at Amazon, maintaining that thing, your structured query language structure is a little bit more complicated than I've alluded to, because you have to identify the database source, you identify the schema that you're going to use, which simply is identifying which of the multiple tables are going to be available to that query. So schema 1 could be these three tables. Schema 2 could be two different tables. Schema 3 could be all 5 tables, and so on. So in our example here, we only have one scheme and these three tables. Tables themselves are named SP and SP. And since they're made up of rows and columns, the rows are records and the columns are fields. And they're meant to be understood as follows. So table S is suppliers under contract. You can read that faster than I can say it to you. So I'll skip to table P, which are the kinds of parts, and SP is representing shipments in this case. So real databases are obviously much more complex than this toy example, but we can make useful observations on the toy. The three tables are the schema, and or framework is a better word probably than schema. And at this point, it's also our only scheme. And we'll name the entire database in the scheme parts as parts. So let's suppose we wanted to represent that database in a data frame type structure and using primitive Python. So if we have a table, immediately our mind comes to lists. Lists are collections of things that are somehow related. So we can have a list named parts, and list of parts has the first record, which are the headings of each column. The next 6 records are the parts lists. We have a list called suppliers and our shipments list. And so there's nothing new there. You've all seen this and done this in some aspect in labs or homeworks. So you can think of a database at this point as a collection of lists. In each of these tables, there's columns. Those are the fields, records. Now let's suppose we want to query our database. So let's decide we want to list all the parts whose weight is less than 13 units. How would you proceed? You could give up and go home. We could hire somebody to do it for us, or because in this class we're going to beat it into ourselves to figure out how to do it, we would have to go through the following important computational thinking steps. We have to somehow instruct it to choose the correct table, probably the parts table. We would have to construct some way to search to find all instances of parts with weight less than 13. You actually know how to do that. That's one of our if constructs. We want to search the entire table so we don't miss any parts. That's a repetition construct. And finally, we want to print the results. So it could be something as simple as for I in range 1 to the length of parts. Now let's parse that as a loop operator. That's pretty trivial. It's getting the length of the list named parts. Since we're not specifying which axis of the list, it's going to use the outermost axis. And that's going to tell us how many records are in parts. Then we're going to look at the third positional entry in parts, which corresponds to the fourth column, which should be the weight column. And we're going to make the test if the parts table in the ith record, fourth column, which is supposed to be the weight column, is less than 13, then we'll print that row out. And so when we execute that, we get part 1 and part 5, the nut and the cam, each are 12, and let's see if that makes sense. Go back to the original database. So part 1 and part 5 indeed weigh less than 13. If it's only 6 parts, you could do this just by looking. But then think back to our picture of the disassembled car. Probably more than 6 parts, right? Be cool if you had a car with 6 parts. 4 of them would be the wheels. Actually, 5 of them. You'd have 5 wheels. You have the 4 wheels that make it go, and then the wheel that points it. And I guess the 5th part would be something to sit your buttocks on so that you could operate the car. They don't make 6-part cars. So we've done the we've identified the parts by weight. So we've listed all the parts whose weight is less than 13, but now we want to modify the query so that we're only listing the part number, color, and city. The first part of the query doesn't change very much. What we send to output, how we complete the transaction, is where we make the change. In this case, we instruct it to return the part number, the part color, and the part city. And we don't want to see the rest of it. So there's another query. Now let's suppose we want to modify the contents of one of the tables. So in this case, we want to delete all instances of the suppliers with status 10. And then for the remaining suppliers, elevate their status by 5. Again, I have no idea what status means in this context. So again, our query is constructed the same way. Pick the correct table, construct the search, perform the indicated operation. In this case, if it's not equal to 10, copy the row. If it otherwise, we skip it and then delete the original table, rename the temporary table, and then continue. So now that particular query starts to get a little bit complicated, especially if I press the wrong buttons. So in this case, because we're doing this in primitive Python, God damn it, just do what I tell you instead of what you want. All right. Our first entry, I'll try one more time, then I'm going to give up. Sweet. We have to create space to store our intermediate operations. So in this case, we create an empty list. And now we're going to look at the suppliers list and just print it. That has no utility for this query. And then we're going to, again, look at the suppliers list and identify the cases where suppliers is equal to 10. So its status value is equal to 10. And notice we're not putting status in there anywhere. We have to actually know the structure, know what the index is. So clearly that's something that would need to be improved if we need to do this a lot. And then finally, slice the sublist, and store it into temp, and then attempt to rewrite the original, and then we'll print the replacement. So you've done stuff like this in lab already. And so we started with this list, which had 5 suppliers in it. And then after, so the query occurred between this and that line. After we have updated the database, it now only has 4 records. And sadly, Mr. Jones in Paris lost their contract. And that's just how easy it is to get fired in the modern world of databases. Now suppose we wanted to find how many parts are coming from London. Again, we would construct a query. And again, if we're doing it in primitive Python, we, the database administrator, have a lot of work to do. We have to code that and test it before we commit to it. So instead of writing our own scripts, which is cool if it's just a single database for a very specific use, in which case I would advocate that you use whatever will get your job done and move on. Instead of writing our own individual scripts, which would be unique to each database schema, the Python community created a module called Pandas. Now, it got its name because most things on the planet are made in China, and their national critter is a panda bear. That's not really how it got its name. The actual name is the contraction of panel data structure. So that's how the word pandas comes up. So you probably have now immediately noticed something kind of funny about Python. Practically everything is named after some kind of animal or has some silly name. That's by intent, because most of the professional computer programmer maintainers that build these things are freaking crazy. And they do that as a joke on the rest of the world. Rather than be mad at them and say, make the thing more sanitized and professional looking, just adapt to it. So it's kind of cool that you have stuff named after snakes and panda bears. And then we had Dusty Functions, which is named after my cat. So yeah, just adopt it right now. Get into naming stuff after animals and playing little jokes on people. Okay, so what you're going to learn in lab today, because I'm actually 2 minutes over, is you're going to go through about pandas. You're going to learn about the data frame. Pandas should work for you all as is, so you'll have to do the import to bring it to life. And you're going to play with some various examples of pandas. So I will see you in about 10 minutes. Thank you for your attention. Have a great day. If you are going to job fair today, good luck. I hope you find an internship that pays you handsomely so that you have enough money to come to school next year and keep me employed. We're all in this together, you know.